Another example of a linear amplifier, and so remember, a linear amplifier needs to have the condition that it stays in saturation for both the DC operation and the AC operation. So for the DC, we need to check what the voltages are and do the comparison. So we know that going through this is going to be the same current as flowing down here. So 3 milliamps goes from here through here. And if we take a loop to determine what V out is, or VD, it's going to be a plus 5 and then a minus 3 milli times 3K. That gives us 5 minus 9, so we get VD is minus 4. The input is given here as V sig is a minus 4 plus 300 millisine omega t. Since this is connected directly, there's no capacitor, that DC value is going to be seen here, and so that's going to be a minus 4 at your gate. And then we said this one is also a minus 4. So the conditions for saturated, we need VGS to be greater than or equal to VT. And we also need VD to be greater than VG minus VT. And in this case, VT is 2. So we get VG minus VT is minus 6. And we have that VD is a minus 4. So that is going to be true. And we don't quite know what VGS is because the VS value is determined from VGS. So we need to determine what VS is. So we need to determine what VS is to determine if we are still on. So we had a minus 4 at the gate and we need to determine this VS. We do that by setting up the ID equation. We know the current, 3 milli. We're given the Kn prime W over L of 2 milli. And then we need to solve for VGS minus VT n squared. This becomes a 1 milli, and then we can bring it over to this side. So this 3 milli divided by 1 milli is 3. And then we have the square root of this is going to cancel out with the square portion of this. So we have VGS minus 2. We bring 2 over to the other side, and we have plus or minus 3. So we have 3.73 or 1.27. This one is less than VT, so it's not this one. So 3.73 is going to be our VGS value, and it is greater than VT, so we can say that yes, this meets the conditions for saturation. So now that we know the DC conditions do turn it on and keep it in saturation, we need to see what the AC portion is doing. So we draw the hybrid pi, and we need to know GM, and GM we can get from that VGS value. And then the output, the current flows this way, so it's a plus minus, so we're going to get minus GM VGS times 3K. And VGS we see is indeed just V sig. So we can divide the V sig on the bottom and we get a V out over V sig, which is our gain of minus 10.3 volts per volt. So knowing the gain is minus 10.38 volts per volt, we can multiply that by the AC portion, which is 300 milli, and that gives us a minus 3.114. So the total equation at V out will be the minus 4 minus this 3.114 sine omega t. So we want to check at the peaks because that would be the condition of their maximum and minimum. So for VG is minus 3.7, you're going to get the output VD at minus 7.14 because this is inverting, meaning that when you put in the highest value, you get the lowest value out. So VD will be minus 7.14, and then we have to compare the VG minus VT. So VG is minus 3.7 minus 2, so that gives us minus 5.7, but that is greater than V out. So therefore, this is not saturated in this position. For the other side, which is VG at minus 4.3, we get out that V out is a minus 0.86. So the conditions here would be minus 0.86, and that is greater than the VG minus VT in this case. So we do have to say that it's not linear though, because it does move out of saturation for one side of this signal. This concludes this solution. Thanks for watching.